Hi, my name is Kolja. I work at the Open Science Lab at TIP Hannover, and today I want to inform you about our current progress in applying a retrieval augmented generation system in the MediaWiki framework. First of all, we are using Wikibase for research. It's an installation pipeline that we developed in the last year for easy setup of MediaWiki configurations like plain MediaWiki, Wikibase, Semantic MediaWiki, or Semantic Wikibase. It's a Docker-based setup, which simplifies the whole installation process. We're using configuration files to select what you want to have installed. It also has an included MediaWiki extension management and some features for importing and exporting data and updating your whole system. It's open source and provided by the Open Science Lab, and we planning a long-term maintenance of the system. So check it out. Wikibase for research is mainly installation process of this whole components. So installation of a Docker-based infrastructure with MediaWiki running, and then you select via configuration the extensions that you want to install, and also we have the feature to install external services like OpenRefine or the Wikidata Query Service, Elasticsearch, and so on. And the advantage here is that you separate your project data from your project tools. And in this specific talk, I talk about these new features here. We are currently providing integration of our antelope annotation service to provide semantic annotation of data within Wikibase, and we are supporting retrieval augmented generation using llamaIndex service. So first of all, what is retrieval augmented generation? It's a method for context-based question answering. So instead of asking a question or providing a prompt directly to a large language model, we want to use context data, for example, to answer domain-specific questions. And also we want to avoid the common behavior of large language models of hallucination, because large language models are trained on big data, but it's hard for these models to generate data that was not in the original training data. So when we ever have specific research topics and domain-specific data, it's hard for a large language model to answer that, and that's where RAG systems trying to offer a new possibility. So there are several strategies some can use. So as you saw here, we need this retriever component that retrieves data from our context database. And the strategies we are using here are mainly based if you have unstructured data or structured data. So unstructured documents, for example, you could use semantic search, which is normally that you split these documents into smaller chunks and use word embedding to index them. If you have, or you can use summarization systems to provide a summary of these large documents and work with these. If you have structured data, you can also use semantic search. For example, you can use word embedding on your nodes in your knowledge database, or you could also, if this is a graph database, use a system that translate your question into a query language like SparkQL or SQL, depends on the database you are using, to query then this data. And for sure, there's also strategies to transform unstructured documents in structured data. This is a task of information retrieval. Okay, let's have a look at a specific RAG strategy example. So first of all, we need to index our data. Let's assume we have unstructured documents. We will then select each document and apply a strategy to break it into smaller chunks. This could be, for example, in a web page that you say every paragraph is a chunk, or you could say in a whole text, each chunk has a fixed size. So there are several strategies you can apply, and it depends on if you more want to summarize the topic of your document or if you want to have access to the smaller information parts. Each strategy has pros and cons. And then we would use here, for example, an embedding model to translate each of the chunks into a vector space. So in the end, each chunk has a specific position within this vector space, and the embedding model is used to make the positions in the vector space so that semantically similar chunks are near to each other. In the next phase, the user will provide a question, and we are using the same embedding model to translate the question into the vector space. So then also the question has a position in this vector space, and then we will retrieve the neighbor nodes. So we will search for chunks that are most similar, semantically similar to our question. And our hope is then that these are the relevant chunks that contains information to answer the question. And then in the end, instead of providing just the question to the large language model, we provide the question, the relevant chunks, and the task to generate a meaningful answer using only information from the chunks. And this answer can then provide it to the user. Okay, in the MediaWiki context, the type of our data depends on the extensions we installed. So for example, if we are using only plain MediaWiki, we will most likely have plain wiki pages which containing text. So this is unstructured data. But we have also MediaWiki categories, which are kind of structured data, but it's a bit of half structured data, I would say. If we are using Wikibase, it's the opposite. We have items and properties which are saved as structured data. And normally we don't use Wikibase MediaWiki articles, so we wouldn't have unstructured data here. With Semantic MediaWiki, we have structured data, like the semantic properties, but these properties are saved within the wiki pages. So this is also kind of a mixed content we have here, but we have access to these properties via APIs, for example. And we also have here the unstructured data. So the charm is here that we have the structured data properties, and we have the final result, like an wiki article, which is extended via semantic queries by the data out of the properties. And if we are using Semantic Wikibase, which is a combination of Wikibase and Semantic MediaWiki, we will also have both. We have the structured data out of the Wikibase, and we have the wiki pages extended via Semantic MediaWiki queries to have the final results. As you see, as we are need a lot of strategies here to handle this this various cases, it's best to use a framework. So we decided to use the llamaIndex framework for our RAG system. It's a large framework. There's open source libraries. It has a large community. It has a large support of various data sources, models, indexers. So it's a good base to start off. And our opportunity was that we had an already prototype that was developed at the TIB by Alexander Gezin, which was the integration of llamaIndex in MediaWiki to use articles as unstructured data. And our goal was to integrate llamaIndex into Wikibase for research. So the architecture of the whole system will then be that we have within Wikibase, you have several containers. For example, you have your Wikibase Docker container, or your Wikidata query service is a Docker container. And then we will have just another container which contains llamaIndex. And llamaIndex is combined then with Flask. Flask is a Python library for providing APIs. So this will then allow us this allows to communicate with llamaIndex, and this communication can be in various ways. So for example, we could include a web form into Wikibase or into a MediaWiki system, so really embedded using widgets or gadgets or plain JavaScript to access the rec system. But you could also use the form from externally. So like providing a single web page that communicates over the internet to the rec system using data out of the Wikibase. So there's a lot of possibilities for integrating this. And also it is possible for sure to use this Docker image that we create without Wikibase for research. So in Wikibase for research, it's especially easy to use or to install, but it's also usable as a standalone component. Okay, let's have a look at a specific case study. So we test this on one of our projects. It's a project about manor houses in the Baltic Sea region. This is built on a semantic Wikibase, so we have data within the Wikibase, but we also use this data to display it using semantic MediaWiki queries, like you see here. For example, displaying the owners and the main data in a nice way. But in this system also we have a lot of research articles, so a lot of text data, unstructured text data. So this is a great example of a project where you have both type of data and a very domain-specific content that a normal large language model wouldn't be able to answer. And if we use our current RAG approach, it's a German Ladama model we used. So I translated the answers here into English. There we are using the unstructured data from the articles that are chunked via HTML tags. So here for this case, we use just the TD tags because we have a lot of tables, table formattings. So we didn't need to really identify the meaningful content. But there are other strategies for this as well. So for example, if we ask simple questions like who owns the manor house Christinehof, we get a good answer that it was owned by the Piper family, and this is exactly what we want to achieve with a large language model, because as we see here, the information that is provided is that there is more than one owner over the years, but the large language model is able to retrieve the information that these are all persons from the same family, and then gives us the information that it's overall owned by a specific family. If we ask for a specific year of building, we get the exact building here, because it was stated in the text at some point. But if we try to build more complex questions, like here, for example, I built a question which is more like a Jeopardy style, like, okay, which manor house was built by the widow of a man who played a significant role in the Swedish state apparatus? And then we get an answer like Hedvig Mörner built the main building of Stola Manor. And this is not completely wrong, but it's not the best answer. So the best answer here would be the manor house Christinehof, because in the text it's stated that the husband played by himself a specific role or important role in the Swedish state apparatus. But here the large language model retrieved another information. The model retrieved the information of Hedvig Mörner, and in the text it stated that her husband, after marriage, automatically became the brother-in-law of Carl Gustaf Mörner, her brother. this man served as a governor in Western Sweden. So her husband is has implicitly maybe a significant role, but it's not completely correct. And here we see the the things that we cannot achieve yet. Maybe we need bigger models out of it. We need better strategies, and the quality of the results we get here are completely based on the strategy and how good we implement the RAG system. So in our current state, we have a running prototype. We have our indexer, which can access. So in the Mainer House project, we access the wiki pages via GET requests, and then we use HTML tags or HTML classes to retrieve chunks out of these wiki pages, and then we index it using word embedding to save all these chunks in a vector space. Currently, we are working on how we can integrate Wikibase data, so the structured data. We have a knowledge base in Wikibase, and in llamaIndex we have a type of this type of graphs are supported. It's called a property graph, and what we do here currently is that we clone Wikibase into the out of the box featured property graph store. So this is a in-memory database holding graph data. So this is the easiest way to do it, but it's maybe not the most performant way or the best way. So these are the things we want to improve. And here we access not the data over GET request, because then we would need to parse it. We use the MediaWiki API and Wikibase integrator to access the items and properties directly. But then again, we can use these nodes and, for example, save it via embedding in the vector space. And one important feature of this prototype is that there's also the possibility for updates. So we can use MediaWiki hooks if the Wikibase, for example, is updated or wiki pages are updated, so that we can rerun the indexer on specific documents. In this example, we use the vector index, like using word embeddings to save our data. But the good thing here is that llamaIndex supports a lot of other indexing strategies. So for example, we could use a keyword table index, which means out of the query, we use a large language model to retrieve keywords, like for example from a controlled vocabulary, and via these keywords identify the nodes, so the documents and chunks and items that are relevant, and then using these to generate the answer. Or we can use a summary index, which are just summarize a lot of documents to answer the question. So this is more for topic retrieval. If we have hierarchical data, you might want to use a tree index where from the query a root node is identified, and then you use some or all of the children to generate the query. And here for Wikibase, the property graph index is the most matching feature that we want to use here. And all of these indexes are out of the box provided by llamaIndex, so we can just use them, but we are currently not using them all. And the future task would be to integrate them and activate them via configuration, so you don't have to change any code. If we look at the Wikibase retrieval methods, so how do we retrieve data or chunks out of the Wikibase? We could use some of the existing methods from llamaIndex. For example, the synonym retriever. So if the user states a question, we try to generate synonyms out of this text and find relevant nodes using keyword match, and then using the neighbor nodes as relevant nodes to create then our answer out of that. Or we could use also a vector context retriever, so like translating our items and properties from Wikibase into a vector space, and then using the query to identify the most relevant nodes. But there are also other methods, like, for example, you can use text to cipher, which means if you have your data in a property graph store, you can use a large language model to generate a graph query language, here cipher, to build a query to retrieve the relevant data. So your question, so this would be mainly the same way, like if you go manually to ChatGPT or any other model and say, okay, I have the following question, please write me a Cipher query or an SQL query to retrieve this data. The good thing here is that normally the user doesn't know the data model. But as this is server-based, we can provide the large language model with information about the Wikibase data model. So for example, with a schema of our knowledge graph, or with controlled vocabularies that should be used. And in the end, we could also make it more structured, like using templates. So for example, we can build or pre-build SparkQL queries, for example, a SparkQL query that will retrieve all the relevant information about a person. And then when the user enters an answer that we can identify that it's related to persons, we just ask the large language model to retrieve the relevant parameters out of the question and fill it into our SparkQL query. So we then get a standardized answer that we can also display in a nice way and structure and so on. And for example, future way could be, instead of using these out-of-the-box models using Cipher, one could also write support for SparkQL, for example. So to ask the LLM to write a SparkQL query using the Wikidata query service, or to write a Semantic MediaWiki query and using the MediaWiki API to query Semantic MediaWiki properties. So these are all very interesting things to do. And as you see, we have a lot of good support to start here. Okay, where do we stand? So the current features are that we have within Wikibase like one-click installation of our RAG system. You can change the models, you can use local models, but also very interesting, you can use models from Hugging Face, so like online models. So you can change, for example, the models depending on the language which is used in your system. We support the usage of unstructured and structured data, which is very interesting in the MediaWiki framework. And the interaction with the RAG system can be via UI or API. It can be fully embedded in the Wikibase or in the MediaWiki, but it can be also on the standalone website. And llamaIndex also supports CPU or GPU processing, depending on which hardware we are running this. Current challenges are specifically the performance of model inference. So we have a quite large response time if you run a local model like 7 billion Llama version 2 model on a laptop. Depending on the length of the answer you want to have, it's currently about between 30 seconds and 1 minute to get a response. So this really is more of, okay, it's better to run it on a server, maybe with GPU support, but it would be cool to bring the requirements here down so it's really fast and usable on every daily machine. And also a challenge is, as you saw, we have a lot of RAG strategies from llamaIndex, how to make this configurable in a good way so it's easy to use. I mean, it's good to have an out-of-the-box configuration that just works, but it needs to be also usable for the end user or for the administrator without changing any code. For the outlook, we will publish this as open source, as all our Wikibase for Research code, and the first running prototype is planned to be published in Q2, so in the next 3 months. It will be usable also without Wikibase for Research. So if someone has an existing Wikibase and want to use the system. So this is definitely possible. A bit more effort, but it's a Docker container, so it should be possible. Also, what would be really cool is to write a Blaze graph store implementation. We are not sure if we are doing this, but it would allow us to not clone the Wikibase data to make it available to llamaIndex, but to just use the existing triple store. So this would speed up things, so it's better for performance and so on. But we need to check if we want to go this route. And also one possibility that is really interesting is a system of auto-reg. So as you see, we have a lot of configuration possibilities here, and all these reg strategies are have a large effect on how good the quality of the answers is you get. And not each user will be able to make out a good configuration, but there are ways to automate this using optimization algorithms, for example, or just brute search. So the idea here is that the user just provide a set of questions and ideal answers, and then you just test automatically different configurations of the system to come up with an out-of-the-box configuration that matches best the example questions. Okay, that's our Wikibase for Research reg approach. Thank you very much. If you have any questions, don't hesitate to contact us. And we cannot provide a Git repository yet, but we will do it in the future. So check out the content below maybe, and we will provide it as soon as possible. Thanks.
Thanks everyone for staying with us in the video recording mode one more time. I think we're really out of time, but if there are any questions, Lucas is here. He can answer questions. I just want to say something, that there was a typo in there, like 2005, that was obviously 2025. And since the presentation is a few months old, we were intending to release the extension in Q2. I think it's technically online, but I think it's not really released. It's findable. It's on Git at least, but yeah. Okay. Questions?
Although we don't really have time, but okay. Well, just a brief comment. I hate to talk about it behind his back, but there was one slide I disagreed with, the one with the structured and unstructured things. I think it would be a check mark, green check mark for all of those, for all 8 cells or whatever.
Okay, I think it's hard to find, but yeah. Mm-hmm.
Okay. My question is that there's already such things for Wikidata itself. There's the Wikidata embedding project, I think, which is like a vector database kind of thing for Wikidata, and then for querying Wikidata via like a Sparkle query via chatbot. There's the Spinach chatbot. It's a sort of a research project, but can you, or have you considered using, trying to use that technology for, Wikibase in general?
So the Wikidata embedding thing you mentioned, I just discovered it actually. And I don't know about Kolja. We didn't talk about since then. And the Spinach LLM, I know it. And we want to, like Kolja also said, like these approaches are something we want to do, like to also do Sparkle queries and to not just rely on the chunking and then like retrieving through a vector store. But we didn't come to that yet.
Okay, I think maybe we should just move on to the next presentation.